Welcome. Today we're going to talk about average atomic mass. We're going to start off by talking about what a regular average is. So let's imagine that we're in the classroom and we're counting the possible ages. Most of the students are going to be 15. There's going to be a few 16-year-olds and maybe a 17-year-old. And then, of course, there's also the teacher, and I happen to be 52 years old. If I was going to do a straight, simple average age of people in the room, I would list all of the possible ages. There are four of them here in the list. Add them up and then divide by four. And I would get an average age of 25. So this doesn't really seem correct. And for good reason. There are a lot more people who are age 15 than there are age 52, right? So that should show an average much closer to 15. Well, the way we take that into account is we do something called a weighted average. A weighted average is the way we do average atomic mass when we look at elements and the isotopes of those elements. So let's do the same thing again, a weighted average. And in the class that I chose, we have 21 people who are 15 years old. We have three 16-year-olds, one 17-year-old, and of course me, 52 years old. If we add all of those up, we end up with a total of 26 people. Now, getting the percentages would just be taking the number divided by the total and converting into a percent. It works out to about 80.8% of the people in the classroom are 15 years old. Now, I've done some rounding here, but it's pretty close to that. 11.5% are 16 years old, 3.8% are 17, and I'm the other 3.8%. The total there is 99.9 because there was some rounding. But in order to do a calculation, we need the decimal number. So we need to take the decimal point and move it over two places to the left. That's how we convert a percent into a decimal number. So when we take this decimal point and we move it two places to the left, we end up with 0.808 or 0.808 because we've moved the decimal point two places to the left. For that, we then multiply by 15 years old and we end up with 12.12. We do the 11.5% the same way, move the decimal point two places to the left, and we get 0.115. Multiply that number times the 16, and we get 1.84. Now for 3.8, we need to move it two places to the left, but there aren't two places to the left. So we have to add a leading zero here in front of the 3. So we get 0.038. Don't forget that. There is that zero right there, and without it, you've got the wrong number. So the 0.038 times 17 gives us 0.646. And we have the same 0.038 for me times 52, and that's 1.976. If we add these numbers up, we end up with 16.582. So this is now the average age in the classroom. So this is much closer to 15 than it is to 52. It's certainly not 25. So this looks like a much more realistic answer. Now, of course, the fact that most people are 15 and only one is 52, this 52 has a much greater weight. If we were to look at just the students and knock the teacher out of the equation, then our average goes down to 15.2. So we're much closer to 15 than we are to 16 or 17. But the average always has to fall somewhere between the smallest and the largest. And both of these numbers do. If we include the teacher, this number is between the smallest and largest, and this number is between the smallest and largest. It's important that you know that these percentages, if we add them up, they should come out to 100% or very close, depending on rounding, 99.9 or 100.1 or something like that. But these numbers here, we can also do a check on these. These numbers should add up to 1. So just like percentages all add up to 100, these fractions here, or these decimal numbers, which are the relative abundances, these should add up to 1. So let's look at chlorine. Chlorine has two stable isotopes. One of them is about 75%, and the other one is about 25%. So about 3/4 is this isotope, and 1/4 is this isotope. The first isotope has an atomic mass of 35, and the other has an atomic mass of 37. Well, right in between 35 and 37 is, of course, 36. So would it be fair to say that the average is 36? Well, hopefully, after looking at the last example, your answer is no. There are a lot more of the 35s than there are 37s. So the answer should be much closer to 35 than it is to 37. So definitely not halfway in between. Let's look at the math here. So for chlorine, we start by taking the 75% and converting it to 0.75. And then we'll multiply it by the mass number for the isotope chlorine 35, and we get this. Then we'll take the 25%, convert that to 0.25, and multiply it by the mass number for chlorine 37 is 37. And we get this. We add these two together, and we get 35.50. So it's clear this is closer to 35 than it is to 37. It's not halfway in between. It's closer to the larger relative abundance, the isotope with the larger relative abundance. And that'll always be true when there's two isotopes. If there's three or more, well, it depends on how they're spread out. But it'll always be somewhere between the smallest and the largest. So it has to be between 35 and 37. And this right here meets that requirement. Let's look at another element. This is carbon. Carbon has two stable isotopes, carbon-12 and carbon-13. There's also carbon-14, which is found in nature, but it's very, very small. So we're not going to count it here. Carbon-12 in nature, it has an abundance of 98.93%, which means most carbon is carbon-12. A tiny amount, about 1%, 1.07%, is carbon-13. So let's do the math. First, we have to convert 98.93 into decimals, so we just move the decimal point over, and it becomes 0.9893. We multiply that by 12, and we get this number right here. We do the same thing here. We move the decimal point over 2 places. Remember, we have to add a 0, and we get 0.0107 times carbon-13, and we get this number. When we add those up, we have 12.0107. So our average for these two isotopes is 12.0107. If you look on your periodic table, you'll see that the average is 12.011. So really these two numbers are the same. If we were to round this number off right here at the thousandths place, they would be exactly the same number. And indeed, these two numbers, since they round to the same thing, we can consider these to be the same number. Now, often isotope data is arranged in a table form like this one here. Here we have isotopes, copper-63 and copper-65. Those are the two stable isotopes of copper. And we have the abundance over here, the relative abundance or percent abundance. And in the middle here, you see something new. And this right here is the mass. We may think, oh, I thought the mass number here after the isotope or after the element name, that was the mass, copper-63. But here you've got something that's really close to copper-63. It's 62.929, so it's less than 1% off, less than 1/10% off, really. But it's not really a whole number like the mass number after the element name is. Well, in reality, everything is based on carbon-12. And so when we do real measurements of real atoms, only carbon-12 is exactly 12. And that has to do with the fact that, first of all, you already know that protons and neutrons don't exactly weigh the same thing. So adding them up as if they were whole numbers is not precisely correct. But there's some other stuff going on in the nucleus that has to do with the energy that holds it together that we're not going to study in this unit. But But the point is, they're not exactly whole numbers when we measure them, except for carbon 12, which everything is based on. And that's where we get this atomic mass unit, where carbon 12 is equal to 12, and everything else is based on that. So atomic mass unit is kind of a made-up number, but we use it as a unit when we're talking about the weight of a single atom. So we're going to use this number instead. Whenever we have this number with units, we're going to use it. If we don't have it, we can safely fall back to using the isotope's mass number, 63 or 65. But these numbers are very close to that, and they'll give us a better answer. We'll start by looking at the first one, copper 63. It has 69.17% abundance. So we have to move that decimal point over 2, and it becomes 0.6917. We'll multiply that by the 62.929 atomic mass units, AMUs. We're going to include the units in here. Make sure to show your units whenever you're given them. And then we'll do the next 30.83%. We need to convert that, move the decimal point over 2 places, and multiply that by the second mass here, 64.928. After that, we'll do our multiplication, and we end up with these two numbers. We add them up, and we have 63.545217 atomic mass units. Clearly more significant figures and digits than we need. In your Canvas quiz, it says round to the hundredths place, so we would draw a line right here and not report anything after this, so it'd be 63.54, but this number right after the last digit we're going to report, it's a 5 or more, which means we need to round this up. So we would report 63.55 if we were rounding to the hundredths place. The last thing we're going to do is a word problem, because we often get isotope data in the form of a word problem on a test, for instance. And they're not as conveniently organized as a table, but they are pretty easy to read when you actually dig into it. The key is that the numbers are always next to each other. So a percentage and a mass are going to be side by side. In this case, the first number, 78.99%, we convert that to a decimal, and we'll put that down here. It's followed by the mass. So we'll put that right over here. The next number, 10%, we'll put it down here after converting to a decimal, is followed by its mass. So we'll put it in. And then our last percentage over here, 11.01%, move the decimal over twice, and we'll put it down here and take the last mass and put it there. So the numbers all come in pairs. We go through and we do our multiplication, and we get these numbers over here. Now, you may think we're doing a lot of writing. Do we need to keep all these significant figures? And the answer is yes. We should never round until the end. So at the very end, we'll round these off. But if we round too early, we may make our answer be different than it should be. If you want to avoid all of this, there's a trick. Your calculator knows the order of operations, and multiplication happens before addition. So if you do the first number times the second number, and then instead of hitting the equal sign, hit plus, and then 0.1 times 24.986 plus 0.1101 times 25.983, and then hit the equal sign, and you'll get a total down here, but you won't have to have all of these intermediate numbers. And that's totally acceptable for showing your work, as long as you show these numbers here. The decimal numbers and the masses are all that you need. You don't need to show me these numbers in between, but if you're not comfortable with hitting the plus between each row here, then you do need to show all of these numbers, and that means you need to write all of the digits that your calculator shows before you round off at the end. So here, We add these up and we have 24.3050798. If we're rounding to the hundredths place, that's this place right here where the 0 is, we look at the number right after that, and it's a 5. So anything that's 5 or more means we round up. So we're going to round this to 24.31. And don't forget the units, AMUs. Since we were given units here, we need to make sure to include the units in our calculations and in our answer.